2020 April question 1. A simply supported reinforced concrete beam has an effective span of 5,000 millimeters. The width of the beam is 220 millimeters. The RC beam must support a 16 kilonewton mid-span point load and a 7 kilonewton per meter uniformly distributed load over the entire span. Use the following information to determine the required reinforcement to withstand the loads. Grade 25 MPa concrete with mild steel reinforcement. Mild represents the letter R again. Mild is represented by the letter R. Mild is equal to the letter R, and then high yield is the letter Y. So barium, the density of the concrete is 2.4. Consider self-weight of the reinforced concrete beam in the calculations. Check if the reinforcement is within the parameters of table 23. So, what do we have? We have the beam, again. We have the width of the beam. Here is our beam. This is our beam. From here to there, it is the overall depth. And then here we have our bars. From the middle of the bars until where the beam starts, we have the effective depth again. Effective depth. And then here we have the cover. Covered, it starts in the middle of this tension reinforcement bar. And then we have the width. They gave us a width of 220. So we have 220. We do not have the overall depth. We do not have the cover. We do not have the effective depth. But we have 220 again. If they've given us the width, you need to apply the basic span ratio again. The basic span formula. The basic span formula again. So what do we mean by applying the basic span formula? We need to assume our overall depth. We need to assume the cover. We need to assume the binder. What else? The main bars again. So first step more, they've given us the span. And then they've also told us that it is a simply supported reinforced beam. So there's a table there. Page 3, man. Page 22. There's a table in page 22. So that table, it has support conditions again. So support condition number 1 is truly simply supported beam. And more on the question they gave us a simply supported reinforced beam like one. So if it is a simply supported reinforced beam, what ratio do we use there on that table? 16 again. So here we are going to say the effective depth is equal to the span divided by the ratio. What is our span? 5,000. And then the span, the ratio?
It's 16.
It's 16. It is 16 because it is a simply supported beam again. So what do we get?
312,5.
312,5. SI unit? Millimeters. So this is the first step. If you are only given the width, you need to apply this basic span formula. You need to apply this. So to get the effective depth, it is equal to span divided by the ratio. The span is 5,000 again, and then divided by the ratio. The ratio you refer to the table. So divided by 16, we get 312,5 millimeters. That is our effective depth again. So for us to get the overall depth, we need to assume. So we need to assume the main bars first. So assume main bar. What else do we assume? The binder. What else? The curve again. So for us to get the overall, okay, before we write the formula, what is the main bar that you assumed? 25 again. So 25 is going to be R25, not Y. It's R because you were given mild. It is mild again. If if you mild, your main bar is R, not Y. I get. But like you mild must.
Yes.
Yes, they said it's mild, so it's R. R25, and then the binder, assume like assume 10. So binder is what? R10 binder. And then what cover did you assume? 25 cow. So first step is to apply the basic span formula again. We get the effective depth by saying span divided by the ratio. We have the span there, which is 5,000. The ratio, you check on the table. So since the support condition is a simply supported beam, the ratio is 16. Again, we get the effective depth. Next step is to assume. You assume the main bar, you assume binder, you assume cover. You assume three things. Main bar, binder, cover. Here, the type of steel, it depends on what did they give you. Is it mild or is it high again? So partially mild, hence we use R25 again. So we need to get the overall depth now. Overall depth. Formula overall depth here. D, which is the effective depth again, plus tension reinforcement again, so it's main bar of tension reinforcement divided by 2 again, and then plus link is the bind again, link is binder, and then plus the curve again. So we have the effective depth. What is our effective depth? 312, comma 5. And then what is our main bar? 25. The formula says we need to divide by 2 again. So divide by 2. What is the link on the binder? It is 10. What is the cover? 25. Calculate. What do we get? Okay? 360. So, 360. So, what do we do? We got 360. What do we do? Why add the 5? Already it's a whole number. So, return to the example. Do we leave it like this or we do something? Why add? Why re-add? You could reflect. Re-add would reflect. Always. The procedure. Okay, so we're gonna use 360 more again. So the 360 here add the 5 here, 365 again. And then after adding by 5, we need to round it off again. So we have 360, here add the 5, we get 365. Then we need to round off the graph. 365. 365 John. You round off to the nearest whole number. After adding by 5, you round off to the nearest whole number.
So if 365, I finally read 365,0.
Mano, round off 365, round it off to the nearest whole number. You forget.
365.
But what's the here? Round off 365, you forget. 370 again. 370. So, to those that are wondering, I'm leveling page 28. Let's go to page 28. Page 28 at the bottom. This is where the code states the following. Lawan and page 28, this textbook. Oh, which textbook is wrong? Page 28 again. This is where the code states the following. The minimum distance between the two end bars should be maintained at a height of aggregate plus 5 millimeter. Hence we add 5 again. So when you get the overall depth, you need to add 5 and then round up to the nearest whole number again. And then in practical terms, if 19 millimeter stones are used, then the minimum will be 19 plus 5. 29 here with a mistake, so it's 19 plus 5. 19 plus 5, eh? 24, and then when we round off 24, you have 20 again. Okay. For 13 millimeter stone, it will be 13 plus 5. 13 plus 5, what does it give us? 17. When we round off 17, you have 18, and then when we round it off, get 20. So when you calculate the overall depth, this is the formula to calculate the overall depth. We got 360 again. Your final answer is not 360. You need to add 5 and then round off. Let's just say we had gotten 355,2. 355,2 plus 5, what will it give us? 355,2 for 360. 360,2, and then if you round it off to the nearest whole number, 360 again. So that is the process. That is how we do it. After getting the overall depth, you need to add plus 5, then round off to the nearest whole number again. So you know our overall depth is 370 again. Let's continue. 370 millimeters. And then after getting the overall depth, we now need to determine the design dead load, the DDL. So reveal our question. Check what do we have? We were given point load, we were given the UDL again. So we need to calculate the design dead load first. The DDL is equal to, what's the formula to calculate the DDL? Volume times density times GA times 1,2 GN again. When we calculate the dead load, this is the formula. It's volume multiplied by density multiplied by GA. This GA is gravitational acceleration again, which is represented by 9,81 times 10 to the power -3. Okay, so let us start. What is our volume? Remember that this is a rectangular beam again. The formula to calculate the volume of a rectangular beam is length times breadth times height again. Okay, so what is the volume there? What is our volume? The volume again, overall depth, and then times the width again, and then times 1. One is our height again. It is always 1. So overall depth there, 0,37. When we substitute here, we substitute in meters again. So it's 0,37. What is our width? 0,22. And then our height, it is 1. So this is the formula to calculate the design dead load. Volume times density times GA times 1,2 GN again. So the volume, remember that it is a rectangular beam again. So rectangular beam is length times breadth times height. The overall depth, the volume over overall depth, which is this one, this is the length again. And then our base, put over the width again, and then the height is always 1 again. So volume overall depth times width times 1, length times breadth times height again. Height, which is always 1. And then what is our density? 2,400 kilograms per meter cube. And then what is the GA? 9,81 times 10 to the power -3 multiplied by 1,2 GN again. What do we get? What is our DDL? I'll calculate it. Okay, after getting the DDL, we need to calculate the design imposed UDL again. So imposed UDL. But let him UDL. Guys, we were given 7 again. So it's 7 multiplied by 1,6 QN again. So, okay, I'm doing so. Point load is 1,6 Qm. UDL is 1,6 Qm. Dead load is 1,2 Gn. So dead load we calculated it directly 1,2 Gn again, and then imposed load we need to use 1,6 Qn. So for imposed UDL, you just take what you were given, which is 7, and then you multiply by 1,6 Qn. You follow that? 9, 11,2 SI unit, kilonewton per meter. And then now we've calculated the DDL, we've calculated the imposed UDL. Which time they gave us the point load again. Now we need to calculate it. So the design imposed point load. Formula imposed point load again. Recalculate again the point load. Point load recalculate again. 1,6 Qm remultiply by 16. We're given 16 kilonewton again. So it's 16 multiplied by 1,6 Qm. Get it from 5. 25, SI unit kilonewton. So more, the calculator, we were determining the design dead load again. So for us to determine the design dead load, recalculate the design dead load, we calculate the imposed UDL, we calculate the imposed point load. You do not always calculate it like this. It depends on what if they did not give you the point load, because you calculate again. Sometimes they'll just give you the imposed UDL. You're going to calculate the DDL and then the UDL fail again. So now we move. After determining the design dead load, we need to calculate the bending moment maximum again. So the bending moment maximum, we have a DDL. Formula calculator DDL king. Formula calculator DDL. Bending moment maximum DDL king. WL squared over 8 again. Also UDL. Leon again. WL squared over 8. But point load, you give WL over 4. I squared and the K over 4 again. Okay, so that's how we calculate the bending moment maximum. So to make this one here DDL. W, what do we substitute? W, we substitute what we got again. For the DDL. 2,30, and then L again. Span again. So span L is the span. So it's 5.0. You substitute in millimeters or in meters? In meters, around 5.0 again. And then we square it divided by 8. What do we get? Seven comma 1875 like this. And then SI unit lima. Kilonewton per meter. Open the long term of 7,187. Give okay. 7,19. 7,19. Okay. And then let us calculate the imposed UDL. So more formula is WL squared over 8 plus WL squared over 8 again. So more WL squared over 8 for the UDL one. So WL is like 11,2, and then L is substituted the span again. So which is 5,0 squared divided by 8. What do we get? 35 fella.
Yeah.
Okay, and then plus point load is WL over 4. So what is the W for point load? 25. Are I calculating the point load now?
Can you make answer?
W is 25,6 again. L again, this pen, right? So which is 5,0 and then divided by 4, right? 32 fell. So R again and then get the bending moment maximum. What is the bending moment maximum? I get this 7,19 plus 35. 35 plus 32. 74, 981.
90.
Okay, 19 and then SINK, kilometer per meter again. Put on motor lost. Lishan. Okay. So after bending moment maximum, calculate the value of K again. So value of K, formula value of K is equal to BM. BM the bending moment again. So keep bending moment maximum is the one that we just got more again. And then divided by F CU V D squared. So what is our bending moment maximum? 74,19. Read times 10 to the power 6. And then FCU?
25.
FCU, what field again? FCU ki concrete ki ela kwa data, so it's 25. And then B ki the breadth again. So here is our breadth, here is our width, which is 220 again. So more than 220 straight. So it's 220, and then DA we are measuring is it the overall depth or effective depth? Effective depth again. So what is our effective depth? 312. 312, comma 5. So let us get the value of K.
I squared.
Square. What is the value for K?
I'm calculating here.
0,138. Oh, okay.
0,138.
Okay, so the value of K is equal to 0,138 again. So more, you need to determine whether is it less or is it greater than value of K prime again. So K is equal to 0,138. It is less than K prime again. Again, K prime is 0,156. So it is less than K prime, which is equal to 0,156. So if K is less than K prime, what does it mean?
Provide tension reinforcement.
Provide tension reinforcement ohm again. Okay. So after the value of K, what do we calculate? The lever arm. Distance of lever arm. So formula distance of lever arm here. Z is equal to D into 0,5 plus the square root of 0,25 minus K. Okay. More value of the distance of lever arm. Is it K or K prime here?
K.
Why K?
K is less than K prime.
So it's 0,25 minus K again divided by 0,9. Is the formula complete?
No.
Since k is less than k prime, you know the formula trying more specify what is it? It is less or equal to 0.95 d. Again, this is not necessary if k is greater than k prime. You only do this if k is less. Again, you more it's less. So if more you got k greater than, you can't say you can't use this formula. If k is greater than again.
Yes.
So now k is less, meaning for our formula is incomplete differential level. Tangent is less or equal to 0.95. D and substituting effective depth. Okay. What is the D? Effective depth equal
312,5
312,5 into 0.5 plus the square root of 0.25 minus what is the value of k?
0,138
0.138 divided by 0.9 less or equal to 0.95. D substitute
312,5
Kupala final answer
253,4 calculating
253,4
1
253,41 millimeter. Yeah. So we are not done again. Answer here is more. It's the answer until here again, right? 253,41 here. So we are not done. Formula really less or equal to. So 0.95 times 312,5 here from where? 296,88. So now we have two values of z again. Renali this value of z, renali this value of z. Now, final answer, now we need to choose the less one again, the least one. So which one is least between this one and this one? 253 again. So now we can one over, therefore the z is equal to 253,41 millimeter. Inside the brackets, one of the least again, one shall we chose the least one. Okay, so after calculating the value of z, we need to calculate the tension reinforcement again. So that, yeah. Our prayer. How do we calculate the tension reinforcement?
AS
is equal to
M over 0.87 FOI times Z.
M, what do we substitute? Bending moment again. So M give bending moment. What is our bending moment?
74,90
74,19
times 10 to the power 6
times 10 to the power 6 divided by 0.87. F what again?
FOI
F.
250.
You told me this 250. Okay, and then what is our Z? 253, 41. What's the final answer? What is AS?
1346.
1346. Fella. 0.054. Are we all getting this one?
Yes.
Are you not SI unit? Millimeter squared again. M squared. Okay. Tension reinforcement AS is equal to? AS is equal to? 1346, 0.054 millimeter squared again. So what do we do here, Fikilemo? We go to the table. Get page mark. 1880. Page 121 again. So I'm over page 121. What do we look for? A number that is close to this one again. And it should be higher than this one again. Okay, so we choose someone. And then another thing, more number of rods. It is preferred for operation from 4 we are holding again. And then if you don't find the range here, it's anything that is close to this one. Come on, not close to maybe 5, 6 again. Let's go 12, number of rods here 12, 11, 10.
Oh, where will you go first?
4 we are holding. 4, 3, 2, 1.
Really?
If you don't get 4, 3, 2, 1, we have 5 and 6. If we start with 3, like a pass. So let's choose one more.
1 goes 7.
1 for 7, 3. That means I can get number of rods.
3 are 25 plus.
3 are 25. Why you have R more?
Because
It's miles again. So it's 3 are 25. Put on my number of rods again. So it's number of rods. And then the type of steel. Then diameter again. So the number of rods is 3, type of steel is R because it's mild steel. The diameter is 25. And then more than 2 1 over AS is equal to 1473 millimeters squared. T squared will be 50 squared. Okay. We are done with the tension reinforcement. What are our lost? Okay, so now let us go and calculate the minimum main reinforcement. Minimum main reinforcement. Formula minimum main reinforcement is 100 AS divided by AC. What is our AS?
1473.
AS more, we do not substitute the one that you calculated again. We substitute the one from the table. So we don't use this one here 13, here 1346 again. We use this one here 1473 from the table again. So AS, 1473. And then what is AC? 375 okay. 370 okay. So AC again, overall depth it's overall depth fluid. AC is length times the breadth. So length again, the overall depth. What is the breadth? It will do it again. So AC is 0, in millimeters. Look at AC. What is the length? 370. And then what is the breadth or width? 220. What do we get? 1,81. So we go to the table. You take which table? Keep page one table. You have another attention to your Page 119. Page 119, there's a table there. So, table here, we are talking about the tension reinforcement, okay? So here we look at tension reinforcement. Here we focus on the table here at the top, not the bottom one. The bottom one we look at compression reinforcement like one. So the tension reinforcement one, you go and look for this formula that you use here. So number 1 and the last one, give the same formula like one. So how do we know for a direction which one? And it says rectangular section in solid slabs. This minimum should be provided in both directions. Is this a solid slab? No, this is a rectangular beam again. So I'm checking here tension reinforcement section subjected mainly to tension. So that is how we know for the the top one and not the bottom one. This is not the solid slab. So now the one that is left, if here number 1 again. Okay. So How do we choose? There's only 250 MPa, only 450 MPa. Remember the question they gave us mild steel, and the mild steel gave me 250 again. So 100 AS divided by AC, which one do we use? 0.45 or 0.8? 0.8. So what you do, draw 1.81, which is your minimum and reinforcement. Is it less or greater than 0.8? It is greater than 0.8. So that is how we do the minimum air reinforcement.
So Menemuki is okay.
The reinforcement is sufficient. The reinforcement is okay. Anything, Sha. The reinforcement is sufficient. The reason why it's sufficient, the tension reinforcement that you get, it needs to be higher than 0.8. Again, it needs to be greater than 0.8. So if it is less, it is not sufficient. Okay, let us move. Push up the maximum one again. Maximum area of reinforcement. You formula maximum area of reinforcement.
4% of AC.
4% of AC. So 4% of AC, what do we substitute for AC? AC regular length times breadth, again, it's overall depth times the width. So it's 370 times 5 times 220. What do we get? 3256. 3256. Okay, so here 3256 millimeters squared. Again, the area, it's the maximum area. So unit area millimeters squared again. So after getting 3256, what do we do after getting the area? How do we know it's sufficient?
If it 1473.
1473. It's AS again. So here the maximum area of reinforcement needs to be greater than AS again. If it is greater than AS, it is sufficient. But if it is less, it is not sufficient again. So get 3256, it is greater than 1473, it is sufficient. Sufficient.